My name is Nilavendran, student ID 512211232225, and good evening to my lecturer, Dr. Muhammad Zaki bin Ayub. Um, Today I would like to present a case study. Title of my case study is AI-driven predictive maintenance for sustainable electronic manufacturing for the course Artificial Intelligence. So, in this presentation, I am bridging the gap between the hardware engineering we do in the labs and the high level AI theories we've studied in this semester. We aren't just looking at software as a separate entity, we are looking at how intelligent brain can save physical hardware from unnecessary wear and tear. This is a crucial step toward the future of smart factories. So this is the literature review and problem statement. In our industry, SMT or surface mount technology, machines are the high speed robots that build the circuit boards for every device that we use. They operate with micrometer precision, but they have a major inefficiency, which is time based maintenance. Currently, factories follow a passive schedule. For example, they might replace vacuum nozzle every 3 months, regardless whether it is working perfectly or not. This creates planned waste where functional components are discarded. On the flip side, if a machine fails before the 3 month mark, the entire production line stops unexpectedly. This unplanned downtime results in massive batches of scrap PCBs. My problem statement addresses this directly. How can we use AI to replace these rigid, wasteful substances with wasteful schedules with a system that knows exactly when a machine is going to fail? Next slide. So my proposed AI application is that I propose a smart sense predictive maintenance system. This involves integrating an artificial neural network or ANN directly into SMT machine's local control unit. The core of this innovation is sensor fusion. We're using 3-axis accelerometers to track micro vibrations in the placement heads and acoustic emission sensors to hear high frequency air leaks in the vacuum system. From an electronic standpoint, I have selected the ESP32S3 microcontroller as the processing heart. This is important because it allows for edge AI. Instead of sending massive amounts of raw sensor data to a slow, energy hungry cloud server, the ESP32 processes the neural network locally at the machine. This ensures that the AI can detect a fault in milliseconds and trigger a shutdown before a catastrophic failure occurs. This local low processing power directly supports SDG 12, Sustainable Development Goals number 12, which is the responsible consumption and production. Go to the next slide. So the benefits to industry and community. The benefits is that um, the implementation is significant. Significant implementations for the industry. We see a 25% to 30% reduction in maintenance costs. We no longer buy spare parts we don't need, and we eliminate the sudden breakdowns that ruin the production targets. For the community and society, the the benefit is environmental. In electronics manufacturing, the precision is the only way to prevent waste. When a machine is 100% healthy, it doesn't make placement errors. This means fewer defective circuit boards containing lead and other hazardous materials and end up in our landfills. A well maintained machine runs with less friction and better heat dissipation. By using less electricity to produce the same number of boards, we reduce the overall carbon footprint of our local manufacturing community. Next slide. Training data and justification. To make an ANN reliable, the artificial neural network, the training data must be robust. Our system uses multiple features, specifically high frequency vibration, to detect mechanical wear and acoustic spectrograms to detect air pressure drops. I'm justifying this model using the AI 41 2000 predictive maintenance dataset from the citation, the UCI machine learning repository. This is a proven dataset containing 10,000 instances of industrial behavior. Why is this critical? Because it includes synthetic failures like tool wear or overstrain. Since we cannot intentionally break um, an expensive machine just to collect data, this verified dataset provides the proven evidence. Our AI needs to recognize real failure fingerprint versus just random background noise in a busy factory. Next slide. So, the overall opinion, success or doom? I argue that it is a success. The research that I've done from McKinney shows that AI driven maintenance increases equipment availability by up to 20%. In global economy, that 20% is the difference between a factory staying open or closing. Regarding a fear, um, the idea that AI replaces workers, data from the International Federation of Robotics suggests that it leads to upskilling. We aren't losing jobs, we are evolving them. Operators are becoming high value AI managers who troubleshoot the software rather than just performing manual labor. It solves the inefficiency gap without sacrificing human element. Next slide. Weak AI versus strong AI classification. I classify this system using the functional domain specificity test. The evidence proves that this is weak AI. While this ANN is incredibly smart at detecting a bearing failure or a vacuum leak, but is completely blind to anything else. You can't ask it to write a poem or anything. It lacks general intelligence. So or it would fail. Maybe if you want to diagnose a human medical condition, it will fail. It is mathematically bound to its specific training data and lacks self-awareness or sentience. It is highly specialized narrow tool, the perfect engineering assistance, but not a conscious being. So these are the references that I have that I've researched for this case study. So in conclusion, the smart sense system proves that AI is a vital partner for the future of sustainable engineering. It allows us to produce more with less waste. My presentation is supported by industrial data from McKinsey, Deloitte, and UCI Machine Learning Repository. So that's all for me uh, for this presentation on this case study. Thank you very much for your time and attention. Um, yes, again, I'm Nilavendran, student 95 122 112 Thank you.